Welcome to the third lecture of linear algebra. In this lecture, we first introduce the concept of partition matrix. So let us start with an example. So assume that we have an n by n matrix A, which is defined to be A11, A12, up to A1n, and A21, A22, up to A2n, all the way down to AM1, AM2, all the way down to AMN. So if we let alpha I for I equals 1, 2, up to n be such that our alpha, for example, alpha I equals to alpha I1, alpha I2, up to alpha IN. So when I equals to 1, it is just the first row. So in this way, if our A is partitioned by this alpha, then we can say, sorry, this is a alpha I since we have m rows. If this is the case, then we say that A is partitioned by row. And on the other hand, we can also partition this guy by column, and we can denote it by, namely, beta 1, beta 2, up to beta n, where our beta I, so beta j, equals to A1j, A2j, up to AMJ, where our j ranges from 1 to n. And also, if our A and B are of the same size and they are partitioned in the same way, so suppose A is partitioned by row or by column, and each A and B are n by n, then we can find that their addition could be also represented by the sum of each partition part. So I'm sorry, this is beta 1, and all the way down to alpha n plus beta n. And also, if we take a k lives in I being a scalar, we have ka could also be represented by the partition form. And partition matrices can also be multiplied by the usual row-column rule. So we shall introduce this by a theorem. So if A is n by n and B is n by, namely, p, then A times B could be represented since A times B means that we are using the column of A to times the row of B. So that really means column 1 of A, column 2 of B, and up to column n of A, and this guy times our row 1 of B, row 2 of B, and all the way down to row n of B. So it equals to column 1 of A, row 1 of A, plus all the way down to column n of A and row n of B. So this is also B. Sorry for that. In dealing with the transpose of the partition matrices, we need not only make each element on the row blocks of A to be the partition matrices, we also need to transpose the elements of each block. Let us see an exercise for finding the inverse of a partition matrix. So if a matrix is of the form A11, A12, 0, and A22, so yes, this guy is said to be, of course, upper triangular, and we say more precisely it is block upper triangular since it is in the partition form. And assume that A11 is P by P, A22 is Q by Q, and A is invertible, that is, its determinant does not vanish. We want to find A inverse. So the solution, first, if we say that A inverse is our B, and B is also partition in the form that A times B be like A11, A12, 0, and A22 times B. So that is B11, B12, B21, and B22. We wish it to equal to the identity, so that is IP, 0, 0, and IQ. So this really offers us a representation for B11, B12, B21, and B22. So that is, we use the row to multiply the column. We have that A11, B11 plus A12, B21 equals to IP. And we also have A11, B12 plus A11, plus A12, B22 equals to 0. We have A22, B21 equals to 0. And we have A22, B22 equals to IQ. So we shall name these four equations by 1, 2, 3, 4 respectively. However, note that in the fourth equation itself is not suffice to show that A22 is invertible. However, recall the invertible matrix theorem we introduced in the last lecture. Since A22 is square and our A has non-zero determinant, so that really means our A22 is Q by Q, which means it has non-zero determinant. So that really means our A22 is invertible. So by 4 and invertible matrix theorem, we can deduce that we multiply A22 inverse. So let us do step by step. So we left multiply the A22 inverse on both sides of equation 4. This gives us this equation. So that really means our B22 equals to A22 inverse. So we have a representation for B22. And now let us move to equation 3. So since we have a representation for A22, and we can multiply, So now we multiply A22 inverse on both sides of 3. So that gives us A22 inverse times A22 times B21 equals to A22 inverse times 0. So this really means that our B21 vanish. And therefore, our equation, so let's go back to our first equation. So let us just copy this down. So in the first equation, we have that A21 is 0, so plug in B21 is 0. This gives us with an equation A11 B11 equals IP. And still, if we name this equation as 5, 5 itself is not sufficient to show that A11 is invertible. So still, by the invertible matrix theorem, we have that A11 inverse exists. So we can multiply on both sides on equation 5 by A11 inverse. And that multiplication is left multiplied. So we have this equation, sorry, missed the A11. So therefore, we have that B11 equals to A11 inverse. So it left us to find B12, and B12 is in the second equation. So we just copy this down and paste it here. So now, since our B11 equals to A11 inverse, so we really have B11. Oh, sorry. So A11 B12 plus A12 B22. So since B11 equals to A11 to the inverse, so okay, so let us just remove this multiplication to the right hand side. So we have A11 B12 equals to minus A12 B22. And now we have that B12. So B22, we have showed that B22 equals to A22 inverse, so we can plug this in. And since B22 equals to A22 inverse, we have that A11 B12 equals to minus A12, that is A22 inverse. And since A11 is invertible, so A11 inverse exists, so we can multiply A11 on the left. And this gives us B12 equals to minus A11 inverse, A12 and A22 inverse. So we have all the representation of B, of each block of B represented by each block of A. So we have our B, which equals to our A inverse, equals to, first we find B11, which is A11 inverse, and B12, we just proved, is minus A11 inverse, A12 and A22 inverse. We also showed that B21 is 0 and A22 equals B22 equals A22 inverse, so that is 0 and A22 inverse. So we have found the inverse of the partition matrix. And know that a block diagonal matrix is partitioned matrix with 0 blocks of the main diagonals. And such a matrix is invertible if and only if each block on the diagonal is invertible. And now, we shall discuss elementary matrices. So, an elementary matrix is one that is obtained by performing only single row operation on the identity matrix. So, if an elementary row operation is operated on an n by n matrix A, the resulting could be written as EA, where E is an n by m matrix that is performed on the same row operation on IM. So what that really means? So that is, if we place A and I side by side in this way, where I is the matrix and I is the identity matrix, and this is the form of augmented matrix, then the operation on this matrix produce identical operation on I. So therefore, we can use this property to find the inverse. So that is, if we have made the left-hand side A to the identity matrix, so that really means on the right-hand side we have the inverse of the A. So we shall introduce an algorithm in finding the inverse. So that is, we reduce the augmented matrix AI, and if A is row equivalent to our I, then we have AI is row equivalent to I and A inverse. Otherwise, A has no inverse. So let us use this algorithm to find a matrix. Example. So we want to find A inverse, where A equals to 0, 1, 2, 1, 0, 3, and 4, minus 3, and 8. So our solution follows from first we construct the augmented matrix. So that is our AI equals to, first is A, 0, 1, 2, 1, 0, 3, and 4, minus 3, and 8. So these are A, and then is the identity matrix. So that is so now we reduce. We want A to be under some operation to be transformed to the identity matrix. So we first observe that this is starting with the first element being non-vanishing and the second element vanish. So we remove this guy so we interchange these two rows, and this gives us 1, 0, 3, 0, 1, 2, 4, minus 3, and 8. On this side, we have this row and this row being interchanged. So we have 0, 1, 0, 1, 0, 0, and 0, 0, 1. So actually they are row equivalent. And know that we do not need to change the sign here since we are not here to calculate the determinant, which is in which the change of rows or columns yield a change of sign. Okay, so let us continue. We now want to remove the 4. So we multiply uh, so we can multiply uh, the first row by -4 and add it to the third row. So the first row remains unchanged. And the second row remains unchanged, obviously. And in the fourth row, we have 4 minus and 8 plus -4, 0, and -12. So we have a 0, a -3, and a -4. And we have to do the same for the right-hand side, where the first two rows remains unchanged. In the last row, we have minus, so 0 and -4 and 0 plus 2, 0, 0, 1. So that is a 0, -4, and 1. And next, we want to eliminate our -3 here. So similarly, we will have 1, 0, 3, 0, 1, 2. And obviously, these two rows remains unchanged. And for the last row, our result is 0, 0, 0, 0, and something. So we multiply the second row by 3 and add it to the third row. So this is a 2. And the same thing happened to the third row of I. So this guy multiplied 3. So we have 3 here, 0. And 3 as 2 minus 4. Oh, sorry. So let us do step by step. So 0 minus 4 and 1. This multiplied by 3. So 0, 3, and 6. Is there anything wrong? So, sorry. So this is only 3, right? So we have 3 minus 4 and 1. Sorry, my bad. And we continue our cancellation. So that is we make this to 1. So we have 1, 0, 3, and 0, 1, 0, 0, 1, 2, 1, 0, 0, and 0, 0, 0, 0, 1, and this is 3 over 2 minus 2 and 1 over 2. And now we can remove these two items by multiply -2 and -3 to the last row and adds back to each row correspondingly. So we will finally have 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we have -9 over 2, 7, and -3 over 2. Here we have -2, 4, and -1. The last row remains unchanged. And since our A is now row equivalent to IN, so we have that two conclusions. First, A inverse exists, and second, A inverse equals to just to this guy. So we're done. And know that it is not necessary to check that if A times A inverse equals to In, since A is invertible. And now we move to the next topic of this lecture. And we shall, in this topic, so this topic concerns subspace, basis, dimension, and rank. So we first define subspace. So a subspace of Fn, or one can replace this guy by Rn, is any site H in Fn such that, firstly, the zero vector lives in H, and second, for all vectors uv lives in H, we have their addition lives in H as well. So that is, the vector addition is closed under this subspace. It contains the zero vector, and it is also closed under scalar multiplication. That is, for all u lives in H and for all alpha in our field. We have that alpha u lives in H as well. So in words, as I just said, a subspace is closed under addition and scalar multiplication. And know that, so if we use Rn instead of Fn, and actually this holds for Fn, I just want to make an example. So Rn is a subspace of itself since it satisfies these three conditions. And another special subspace is the site containing only zero vector in Rn or Fn, and this site is called the zero subspace, since it also satisfies the conditions for being a subspace. Moreover, for V1 up to Vp lives in Fn, the set of all linear combinations of V1 up to Vp is a subspace of Rn. So that is, for all alpha such that, or okay, for all alpha such that V1 alpha V1 plus 2 alpha Vp. And since this is arbitrarily chosen, alpha is arbitrarily chosen, so obviously it's satisfied that for a given scalar, so it obviously satisfies the three conditions for being a subspace. So that is, the set of the all linear combinations of V1 up to Vp is a subspace of Rn or Fn. And we shall denote by span of V1 up to Vp as the subspace spanned or generated by V1 up to Vp by linear combinations. Let us define the column space. So the column space of a matrix A is the site denoted by column of A, which contains all linear combinations of the column of A. So, as we said before, by the invertible matrix theorem, if A is non-singular, then we have that, say, A is n by n, then we have then for then we can actually say that if we take all its pivot positions, So for example, let's suppose the most trivial case that all the pivots lay in the first column. So in this case, the column of A is just equal to this guy, and each one is linearly independent. So in saying linearly independent, we mean that for all, so alpha 1, A11 plus alpha 2, A12 plus all the way down to alpha n, so that is A21 and AN1. So this guy equals to 0 if and only if alpha 1 equals to alpha 2 equals all the way down to alpha n equals to 0, where each of them are scalar in F. So the column space really imply the invertibility of the matrix A, of the corresponding matrix A. And of course, the column space, so um, if A equals to A1 up to AN, and with the columns are in Rm, then the column space column A, it is the same as the span of A1 up to AN. And the column space of an n by n matrix, of course, is a subspace of Rm. And note that column of A equals to Rm, or it behaves like Rm only when the columns of A spans Rm. So otherwise, column A is only a subspace of Rm. And also, we want to introduce the concept of null space. So the null space of a matrix is the set NULA, which contains all the solutions. So it is defined to be all the solutions, namely B, such that AX, all the X, such that AX vanish. So when A has n columns, the solution of AX equals to 0 belongs to Rn, and the null space of A is a subset of Rn. So yes, null space and column space are both subspace of Rn if our underlying number field is R. And now we shall prove a theorem which turns to be very useful. So the null space of an n by n matrix is a subspace of n, of Rn. And equivalently, the set of all solutions to the system AX vanish of unhomogeneous linear equations in n unknowns is a subspace of Rn. So let us prove this theorem. So first of all, we have, since A0 equals to 0, we have 0 ellipse in no space of A. So that is trivial. And now let us take U and V lives in no space of A. So we have since it lives in no space of A, we have AU equals to 0 equals to AV. And by the property of a matrix multiplication, we have A times U plus V equals to AU plus AV, which vanish. So of course, U plus V, so that is no space, is closed under vector addition. And the same thing happens for the scalar multiplication. So for arbitrary scalar alpha in R, we have that A times alpha U equals to alpha times AU. And since U is in the null space A, this guy is 0, so it is alpha times 0, which vanish. So of course it is closed under scalar multiplication. And because a subspace typically contains an infinite number of vectors, some problems involving a subspace are handled best by working with a small finite set of vectors that span the whole subspace. So that is, we want a small site or small space, of course comparing to the subspace, that contains as much information or all the information of the original subspace. And of course, such a smaller site must span the whole space. And this is the motivation for defining the basis. And know that since every space, so Rn is a subspace of itself, so a basis for a subspace of Rn is obviously also a basis for, so let us write this down. So a basis for a subspace H of Rn is a linearly independent site in H that spans H. So when H equals to Rn, such a basis is a basis for Rn itself. And for Rn, we have the basis, the most elementary basis, being 1, 0, 0, 0, all the way down to 0. And E2 equals to 1, so 0, 1, all the way down to 0. And then En equals to 0, 0, 1. So obviously this side, E1, E2, up to En, their span is just Rn. And this is called the standard basis. And now we introduce the concept of the pivot column. So a pivot column is a column in a matrix that contains a leading entry in a row during the process of row operation, row reduction, or Gaussian elimination to our row echelon form or reduced row echelon form. And the leading entry in a row is the leftmost non-zero entry in that row. And now recall that the not very good example I offered here. So yes, the pivot columns of a matrix obviously form a basis for the column space. So let us prove this theorem. So that is, the pivot columns of a matrix A form a basis for the column space of A. Actually, one can prove this as an exercise. I want to offer a remark that we shall be careful in using our pivot columns of A itself for the basis of column of A. This is because that the columns of the echelon form, namely B, are not often in the column space A. And the main reason for selecting a basis for a subspace, namely H, instead of merely a spanning side is that each vector in H can be written in only one way as a linear combination. So that is different. So that is the key difference between the spanning, a side that spans the whole Rn and the basis of Rn. So suppose B is a basis for our H. And suppose that X is a vector in H, and H is generated by basis for H. And suppose X has two representations. So the first is that X equals to C1 B1 plus all the way down to CP BP. And it has another representation by some D1 B1 plus DP BP. So x minus x equals to C1 minus D1 B1 plus all the way down to CP minus DP BP. And since it is a row, so all the elements are linearly independent. So that means C1 minus D1 equals to CP minus DP equals to 0. So C1, so they're mutually equal. So that really means the in if we are using the basis for H, if we find the basis for H, then every vector in H could be represented by linear combination of elements in basis and some coefficients in a unique way. So this is very important since we can use this property to define the coordinate vector. So recall in our most basic XOY plane, in this case, the standard bases are just 0, 1 and 1, 0. So each element in this plane could be represented by a unique way of some linear combination of these two bases. Okay, so let us introduce the coordinate vector. So suppose that B equals to B1, BP is a basis for a subspace H. Then for each x in H, for each vector obviously, the coordinates of x relative to the basis B are those coefficients, are the coefficients of its unique representation, so namely C1 up to Cp, such that x equals to C1, B1 plus all the way down to Cp, Bp. So we can write it in this form to denote, so perhaps this guy is called the coordinate vector of x relative to the basis B. Or we can say it is the B coordinate vector of x. I know that so the map, the correspondence x maps to its basis, p coordinate basis is a one-to-one correspondence. So that is, so it is between H and RP. Sorry, H and Rn. We are assuming that the whole space is Rn and p smaller equals to n. And we see that since it maps to the basis of the subspace, and this coordinate when multiplied correspondingly to the basis forms x itself. And we can see that such mapping indeed preserves the vector space structure. And for such a mapping, we call it an isomorphism. And if there is an isomorphism between H and Rn, we say that H is isomorphic to Rn. So in general, so B equals to B1 up to Bp is a basis for H. Then this mapping actually makes H, so makes H looks like Rp, even though the vectors in H themselves may have more than P entries, but there are only P-independent elements. And it can be shown that if a subspace H has a basis of P vectors, then every basis of H must consist exactly P vectors. So that is, for B is a basis for H, and for C is another basis for H. Then the dimension of B and C must coincide, and this important property leads us to the definition of dimension. So the dimension of a non-zero subspace H is denoted by dimension of H is the number of vectors in any basis for H. And the dimension of the zero space equals to 0. Zero subspace 0 is defined to be 0. So we see that Rn has dimension n. This is well known. And of course, every basis for Rn consists of n vectors. We call that the XOY plane has elementary basis being 1, 0, and 0, 1. So this is a basis for R2. And of course, a plane through 0 in R3 is two-dimensional, and a line through 0 is one-dimensional. Now let us define the rank. So the rank of a matrix A, we shall denote it by rank of A. It is defined to be the dimension of the column space of A. So know that since the pivot columns of A form a basis for the column space, so the rank of A is just the number of pivot columns in A. And one of the most important theorems is the so-called the rank theorem. It states that if a matrix A has n columns, then we have that the the rank of A plus the dimension of the null space of A equals to n. So that is equivalent to say, since rank of A equals to the dimension of the column space of A, so that means the dimension of the column space of A plus the dimension of null space of A is n. So that also tells us that there is a duality relationship between the column space and the null space. Another important theorem is called the basis theorem. So if we let H be a p-dimensional subspace of Rn, then any linearly independent set of exactly p elements in H is automatically a basis for H. So we can technically or theoretically finding p linearly independent elements can form a basis for this p-dimensional subspace H. So this is a way for finding the basis. And moreover, any set of p elements of H that spans H is automatically a basis for H. And now recall that in the last lecture we introduced the invertible matrix theorem, and now we offer more equivalent relationship to that. So this is a modified invertible matrix theorem. So let A be an n by n matrix. Then the followings are equivalent. First, A is invertible. And second, the columns of A forms a basis for our Rn. And 3. Column space of A is Rn. 4. Dimension of column space of A is n. So that really means it is full rank. That means the rank of A equals to the dimension of um, its order. And 5, we have rank of A equals to n trivially. So that really means since the column space and the node space are complement to each other, so we have node space of A is just the zero element, and obviously the dimension of it, by definition, is 0. And note that when A is invertible, the node space of A is this guy instead of empty site. This is common mistake. Since in this case, the only term that makes AX vanish is the zero vector. So it is not the empty space. It contains one vector even though its dimension is 0. So we introduce some properties for rank to end this lecture. So let A be an n by n matrix. We have, firstly, rank of A equals to rank of A transpose. So transposing a matrix does not change its rank. And this is very important since we only introduce the column space and we are right now missing the row space. This offers some insights in introducing the row space and its corresponding properties. The second result is that if we let B be another non-singular n by n matrix, then we have that the rank of A times B equals to the rank of A itself. And similarly, if C is another non-singular and n by n matrix, then we have rank of this time left multiplication. This guy also equals to A. So that means for an arbitrary n by n matrix, once multiplied by a non-singular matrix, the rank of the multiplication equals the rank of itself. And since all the theorems we offered, except one in this lecture, are without proof, so one may prove themselves or convince themselves as an exercise, since it is not too hard to derive a desired result. So this concludes our lecture, and in the next lecture, we will discuss the vector space and subspace. So yes, matrix is only a linear transformation between vector spaces. So we have introduced the matrix, and we need to also introduce the underlying structure, which is called the vector space, and it is the heart of the linear algebra. Thank you for watching, and see you in the next lecture.